So welcome everyone to this talk called YD. It's an opinionated talk on why you should pick the D language for your next project. My name is Atila Neves, and you can reach me on social media and these addresses here. My tour is usually just programming stuff anyway, so yeah. So who am I? Why am I here? Why am I talking to you? So I used to be a PhD student here at CERN in the NH60 experiment before the LHC was even finished. So it was on the SPS, which was the biggest ring that was still working at the time. And we were doing heavy ion physics. And then after that, I realized, well, I don't have to explain to this crowd that I was writing code every day as a physicist. Normally, with normal people, I have to explain that, but obviously not here. And I realized that I was both better at writing code in physics, and I like doing it more as well, and these two things obviously are related to one another. And so I decided well before I finished my thesis that I was going to not do physics again and do IT. And I was lucky enough to get a fellowship in the IT department in the security team 2007, 2008. And that's the last time I worked at CERN. I ended up staying here in Geneva illegally and without a permit because I'm nuts, but it ended up working out for me in the end. And I got a job at Cisco Systems. I'm a software engineer there, mostly C++ in the first project, but also C and Python. And I started dabbling in D whilst I was there. Right now, I'm an independent consultant. My main clients are a hedge fund called Symmetry Investments and the D Language Foundation. And I ended up becoming the co-leader of the D programming language. So I didn't invent the language. Somebody called Walter Bright did. But he brought me in to help him design the language and take it forward. And I'm responsible for the standard library, which is called Phobos. So anything that goes into standard library, new symbols, I have to approve first, and it's on me to basically come up with the design and the vision going forward. So that's why I'm here. And how did I get to D? Because I was an avid C++ programmer. That was definitely my favorite language way back in the day. I spent a lot of time learning its intricacies and have written a code that will make your hair stand on end. You'll even see a slide with some of that code later. Not a lot of it, fortunately for everyone involved. And in 2013, I'd been writing C++ at that point for 15 years. I ended up learning it by myself at home when I was still in university. I did some personal projects with it. I ended up doing my final year project with it. I wrote a game in it, and I just did it for fun at the time. But in 2013, whilst I was at Cisco, I was going through a transition period that kind of coincided with a lot of things at once. So I ended up looking at programming fonts for 2 hours to pick one. I went back to Emacs from Eclipse because at Cisco, everybody used Eclipse and I didn't want to rock the boat, but then I got tired of it. And I went back to Emacs and wrote some packages to have the IDE experience there in Emacs, which is a lot more configurable. I changed from Ubuntu to Arch Linux at the time. I changed my shell from Bash to ZSH. So I was a kind of a fertile ground for changing things about my life. And coincidentally, that year, there was the first real DConf, so a conference about the D language. And some videos started popping up online, and I started watching them, and I got intrigued about the language. Also, by coincidence, a friend of mine and colleague at work had the D programming language book by Andrei Alexandrescu. You might recognize his name from C++ fame. He wrote a very famous book called Modern C++ Design back in the day, which was mind-blowing. And then he ended up getting involved with D, and I'm the new Andrei in the sense that I'm the co-leader of D because Andrei left his post. So this person lent me the book. I read it cover to cover in a sunny afternoon. And then I went, right, I like this. I'm going to start writing some code. So I started writing some code and playing about. And I ended up with 2 projects that I was trying some things out that I'd already done in C++. How can I do this in D, given these things I've seen in these talks? And because of those projects, I ended up applying to go to DConf 2014 in California at the Facebook campus and ended up getting accepted, did a talk there, and haven't left since, apparently. And now I'm maintainer of multiple D packages. And in 2019, I ended up getting announced as the co-leader of the D language. And in 2016, at DConf there, I got approached by someone who used to work for Symmetry Investments and asked me if I wanted to work with him or not. And that's how all this thing started, because he was into D and we use D at Symmetry as well. Also, feel free to stop me anytime and ask questions, because I tried to condense this, but it turned out to be a really big topic. So I'm going to gloss over certain things. I'm sure that will cause confusion. So don't worry about it. Ask me anything. Now, why D? I want to start with the why because I want to start with our values. And this is my opinion. If you ask other people in the D community, they'll give you different things. But because I've learned over the last few years that a list of features does not convince anyone. And it's not really how people are convinced, because the rational part of the brain is not where emotions are, and emotions can't really be expressed properly by the rational part of the brain. They're literally two different systems. And so it's a question of feeling first, and then you justify it later. And so the why, the feeling part, at least for me, is that code should be beautiful. Now, the D Language Foundation itself, we just went through this program called Ivy, which is Ideal Version of Yourself. And over a few weeks, we came up with our Ivy statement, which is, what is our ideal? What is our lofty goal? And it's to enable the realization of ideas by shifting the way programmers think. And so this is how we guide ourselves. Every time we're doing something, we're deciding to do it or not and how to do it. We look back at this sentence to see if we are being true to it. If we're not enabling the realization of ideas by changing the way programmers think, then that's not what we should be doing at that point in time. So that's our big why. Again, code should be beautiful. And again, for me, I think this is what brought me to the language. To paraphrase Einstein, there should be the least amount of code possible, but not less. Because of course, if you write, if you put 1,000 semicolons in one line, you will have a one-line program, but not really. So that doesn't make any sense. So given the why, let me give an example of what I'm talking about when it comes to beauty and terseness, but terseness that's actually understandable. So let's go over this code here. Import SCD is just imports the whole standard library. I don't recommend this for production code, but on the slide, it makes sense because now I can use every symbol I want without having to import the several sub packages. Void main should be recognizable for anybody from C++ with the curly braces, of course. Since C++11 is also being auto, so we're using auto here as well, this type inference. So auto sum equals 0.0. Of course, that's a floating point number, which means that will be the juice's double. And then auto count, because we're counting the line, we're counting average line length, actually. We take standard input, and then we say, I want this by line. So on Windows or Unix, it will do the right thing, depending on carriage turn, line feed, or just line feed, because it knows what platform you're on. So you want by line. You don't want to say split it by \n, because that might not work on Windows, for instance. And then you T, if anybody knows the Unix utility T, this does basically the same thing. It splits the stream into two, do this thing, but then also pass it through unchanged. So we T so that we can sum the line lengths. So this is a lambda in the T. So that bang parentheses, this is a compile time lambda. So line there, I didn't even declare the type because it's a template, so it deduces what it is. So from the parameter line, I go to sum should add the line length to it, and sum is the thing we just declared above there. And then walk length is basically the length. I won't go into why it's called walk length. We can go into it later if you want. And what that does is standard input by line, please add to the length, and then walk the length because I want the count, the final count, because I want to divide. And then right line, which is recognizable to anybody who's ever done Pascal, is basically printf with a \n at the end. Except, of course, this is more like cout in C++, because it will know how to format things. Average line length, and then if there's a count, sum divided by count, if not, 0. So readable, small, does what it says, works. I did actually compile that and try it just in case, because you never know. Slides. And another example that I really like to show is how easy it is to call D from Python. This is literally all the code you need to call all of the D code in a module called myModule. It's 2 lines, and one of them is an import because the library has to come from somewhere. That's it. And it's basically self-descriptive. Wrapped in D, library name because I need to know what you're going to call the Python module that I'm going to spit out, the SO, and then which modules. And by the way, that's variadic. There's only one module there to fit in one line in a slide, but I could put more modules up to any number of modules. And that will make every single D function in those modules and every single D struct and every single D enum show up in Python as if you'd written it yourself at compile time. That's it. That's all you need to do. And it's hard to do this in a language that doesn't have the features that D does. And we'll get to those in a bit. So how do we do this? So the why I've explained, then I'll show the example of what it looks like. So how do we achieve that? How do we achieve beautiful code and terseness and all those good things and shifting the way programmers think, enabling the realizations of ideas? I will go through nearly every single one of them later, so don't worry. The first one is CTFE by default. What does that mean? Compile time function execution. In C++, this is spelled const expr, okay? But it's by default in D. Instead of having to opt in to compile time execution, instead of having to satisfy certain rules, there are rules, but you'll know if you try calling a compile time and it doesn't work. So just do it. If you can, you will. Which changes things because defaults matter a lot. And so that's one of the things that makes this powerful. String mixins allow you to take a string at compile time and then mix it into the current program as if you had written it yourself. That sounds slightly stupid and useless, but it isn't, and we'll see why. Compile time reflection. I can look at types and ask information from the compiler in the language itself, no preprocessor, no other step, no code generation, and ask what types this module has, and then go into the types and see if it's a struct, what are its subtypes, what are the members, that kind of thing. Compile time. Python has this at runtime, Java has this at runtime, D has this at compile time. Anything can be a template parameter, including other templates. Up until C++20, only integers could be template, and types could be template parameters. So the only non-type template parameters were integers. Booleans count because they can convert to integers, that kind of thing. In C++20, they did add a few more other things, but it's still not as powerful as basically any symbol in D can be passed as a template parameter. Import C is the ability to use C code from D without having to do anything else. So there's basically a C compiler within the D compiler right now. We have built-in arrays or slices because they can be sliced like in Python, and associative arrays. Because it turns out when you go for a data structure, it's nearly always give me something sequential I can append to, and give me something that maps a key to a value. Sometimes you reach for other things. Sometimes you want certain characteristics in terms of space and time complexity. But nearly always, this is what you want to do. And of course, Python has this, and it's easy. In C++, you have to import vector and the syntax that goes along with it, or map, or an ordered map, etc. We have immutable and shared qualifiers as well as const in D. So const works similarly to C++, but it's more powerful because you can't take it away. There's no mutable equivalent. And immutable is even worse because the const means I'm not going to mutate this thing by this reference, but somebody else could if I hold on to it. Immutable means nobody can mutate it anywhere in the program. And that's important because of multi-threading. Ranges is something that came to C++ afterwards. And in fact, Eric Niebler at CPPCon 2016, if I'm not mistaken, because I was there in the room, even gave an example from D that motivated him writing the ranges proposal that ended up being included in the standard library now. D has memory safety basically by default, and bug prevention is a big thing as well. So things that shouldn't compile don't, for the most part. When they do, it's a bug and something that needs to be fixed. That's how we deal with it. We shouldn't be letting people write code that's buggy if the compiler knows it's buggy to begin with. So for instance, again, I'm using C++ because everybody here knows it, and it's the most similar language to D. Returning something by reference, which is on the stack inside the function. Maybe if you enable warnings, you'll get a warning from the compiler, but that will compile. And D won't let you do that. And it's also got built-in documentation and testing. So things like Doxygen aren't needed because the compiler deals with documentation. So it already knows how to do these things and then generate HTML from it. And testing as well, there's a unit test keyword that introduces a test. So there's a testing framework baked into the language. You don't need to do anything. You don't need to get anything from the internet. You don't need to import anything. It works. It's bare bones, and so bare bones that two of the most popular libraries for D are testing libraries, but it works without you having to do anything. So CTFE by default, what does that look like? I just defined this factorial function here, which looks familiar to everyone. And what happens here is when I do enum, and I know this is a weird usage of enum, but this makes it a compile time constant. When I do enum instead of a list of values, enum variable means this is a compile time. I can use this at compile time anywhere. This could be a template parameter. And that will get run a compile time and then stuff 120 in there, and that's it. But it came from a function. Of course, this is a simple function, but it has to fit on this client. And square root there is from std.math. I didn't do anything special. There's no special version of it. I just used it at compile time and it worked. because the compiler can interpret that square root function from the standard library at compile time and then stick the value in there. And I can use that as a template parameter if I want to. For instance, I could use that for the length of a static array. But I could also call the same functions at runtime because there's nothing special about them. You'll generate the object code to them, you link them, and then it'll work. But the thing is that this is by default. I didn't have to, there's nothing in that factorial function saying I want to call this from compile time. It's the usage that matters, not the definition or the declaration. So string mixins, the first time I read about this in the book, I thought this was useless because what it said was you can mix in any string known at compile time as if you had written it yourself. And I thought, well, what's the difference between just writing the string? The key words here are known at compile time. That does not mean it's static. It could come from a function evaluation at compile time. So you can generate code at compile time and then mix it in as if you'd written it. And so that's how we achieved that trick of calling D from Python. I was generating a bunch of code and then mixing it in as if I'd written it myself, but the compiler wrote it for me. So the example here is a function that returns a string, takes an integer, and all it does is go return a string that says auto x equals, and then the integer that I just passed in. And if I mix in code 5, it has declared an auto x equals 5 in that scope. So I can assert that x equals 5, even though there's no x there, but there is because I mixed it in. Of course, if I try mixing it in again, compiler error, x is already defined. But again, it's a silly example, not what you do in real life with this. What you do in real life is the Python thing, for instance. Or Excel, for instance, also the same thing. Same 2 lines in Excel to call D from Excel. Same 2 lines. Compile time reflection. Again, silly examples for the sake of slides. There's a structure with an integer and a string. That's all it has. And alias works like using in C++ or, back in the day, typedef. So this is just to make it also short in the slide. So I'm just aliasing members to traits. This is a compiler intrinsic, all members. And then I pass it struct, which is the name of the type that I want to reflect on. And now those members are a sequence of strings, which are the names of the members of that struct. So static assert works like its equivalent in C++. It's an assert at compile time. So at compile time, I can assert that the first member is called the int and that the second member is called the string. And then I can do interesting things with it, like saying, give me the type of the member that's called the string in struct, which is what that penultimate line does. I'm asking for the type of the penultimate member of the struct. And then I'm asserting that it is, in fact, the type is equal to string. So these two things are the same type. It is a bit of a weird expression there that is, which takes some getting used to, but that's how in D you write equality for types. You want to assert that a type is equal to another, they are the same type, there you go. And this would fail if one of them was const. So sometimes you don't care about constness and you have to take that into account as well. But obviously, again, for a talk and a slide, let's just make it simple. So this is extremely powerful because I can look at a module, look at the structs inside of it, and do whatever, generate code based on the types that I find in there and how long they are, and etc. Anything can be a template parameter. So not just types, not just integers. I've imported a meta function called filter there from std.meta. It is also a template itself. Let's not worry about that for now. This second line needs some explanation. This is a syntactic sugar for declaring a meta function. A meta function is a template that takes something and returns something, evaluates something. In this case, it's a template that takes a type and evaluates to a Boolean. So what this template does is it evaluates to true if the size of the type is 4. If it isn't 4, it evaluates to false. And as I previously mentioned, bang parentheses is equivalent in C++ of angle brackets. So it's template parameters. And then I can alias, right? So the types 4 is, I'm going to filter using this predicate called is size 4, which again evaluates to Boolean if the size of the type is 4. And then I give it a bunch of types. Only 2 of those have size 4, int and float. And so I static assert that the length of that thing is 2. I could also print it out when you see the types, but this was easier to also check because I kept copying the code over and making sure this compiled. Any question about this? Because I know that the syntax is a little bit weird. But my point here is that the filter meta function took as the first template parameter another template, which is something very, very powerful. It could also take a symbol, which is interesting. You could take a variable, pass the symbol of it into it, and then there's things you can do with that too. So any symbol is valid. It's extremely powerful, and you can do static maps and static filters like this on types. So you can do functional programming on types as if it was regular programming, except of course the syntax is weirder and there's templates everywhere and takes longer to compile and all of those interesting things. But this is powerful. Now, this is not what people do every day, all day, but it's possible. Import C is a feature that's just barely been released, and there's a C compiler within D. And that allows us to import C code as if it were a D module. And so if I have a C file called cfuncs and I have a square function in there, in a .d file, I could just literally go import cfuncs as if that were D, and that will work. And the D compiler will even compile that C file for you. You don't need to use GCC to compile that separately. You can compile both of those at once, and that will work. Of course, that code there could be C, C++, D, Objective-C, but it's C, and it will work. You can have macros in there, etc. Macros is something that's harder to deal with for multiple reasons, because I wrote a program to translate C headers to D, and macros are particularly interesting because they're not valid C code by themselves sometimes. You need context, and a human can sometimes figure out what the macro is trying to do, but I don't know how to write a computer program that can. Okay. So arrays and associative arrays, it's really good to have this in the language proper. It works nearly as you'd expect. The syntax is more similar to Python, except that associative arrays use square brackets as well. So the first line just declares an array of 3 elements. I can append to that array. So I can append one element to the array, and now the array is 1, 2, 3, 4, sorry. I can append another array to that array. Of course, I can't append an array of strings because statically typed. That won't compile, but these are integers, so that's fine. After I appended that array, we have 1 through 6, and then I can slice it similarly to Python, except the syntax slightly different. Instead of a colon, it's dot dot. So slice from 2 to 4. It's close at the beginning, open at the end, as it should be. And so you get 3 and 4 from there because it's the third element to the fifth, and there you go. And then associative arrays are similar, except you have a colon mapping the key to the value, but they're also statically typed. And so after I declared this, there's special syntax for it, which, for instance, is supposed to be lacking. You have to use the curly braces to initialize it, which works, but isn't as nice as this. And asserting that if I look up bar in AA, I get 2, and then I can also, assign a new value in as you'd expect. That works. So very simple, but it's there. You don't have to need to import anything. It works. Yep.
On line 4, so if you're appending an array to array, what does the compiler do if you have an array of arrays? What does
it won't compile.
Sorry?
It won't compile.
Okay, it won't simply won't.
Because it's a different type. That would be int square brackets square brackets. It would be
yeah. So assume that array was an array of arrays.
Oh, okay.
And then you do an append of an array.
Oh, then you'd get an array of arrays with that being the last element. It wouldn't flatten.
Okay. Okay.
Because the compiler knows what type it is. So Python can't do this. That's why it doesn't append, exactly. Because it doesn't know what the type of the list should be. But since you already know the type, it's an array of arrays, the only thing you can have meant is this. If that makes sense.
So these arrays all have also static length?
No, these are dynamic arrays. You can have static length arrays, but then you'd have to tell the compiler how much it is by bringing square brackets and then the number, and just like in C. Except in C, it's in the wrong place. Here, it would be int square brackets 4 and then the name of the variable, just like in Java. So these are dynamic arrays. I could gloss over static because they don't use that often, but you can put them on the stack, etc. But you can't pass them around, so. And so how are these familiar? I've just presented a bunch of ways in which it's different, but it's so familiar because I made a point of showing everything that was different. I could show you code that, the square function from before is, and factorial, easy to read. It's an ahead of time compiled statically typed language. It supports procedural programming, so it has if and while and do while and for. It also has for each, because it has traditional for loops that work exactly like in C, but also for each that works on, for instance, if you had an array like the ones I showed in the previous slide, you could for each over it, and ranges as well. And functions, so procedural programming indeed looks like it does anywhere else. It could pass for C code, modulo some syntax changes, which even aren't that great. It has C-like syntax that's on purpose. One of Walter's goals was that if you copy C code and paste it into a decompiler, if it compiles, it does the same thing. Unfortunately, that means we inherited a bunch of stuff from C, like integer conversions and promotions that nobody really wants. And the C standard library is available. Even before import C, we'd basically taken the C standard library and written D definitions for them. So you can call it to printf, you can call it to malloc, you can do whatever you want. But they're namespaced because we have a module system. Object-oriented programming works nearly exactly the same as in Java and C#. There are classes and interfaces, it's single inheritance to avoid the multiple inheritance problems. And classes are different from structs, like in C#. Classes are reference types, structs are value types. And interfaces, of course, can only have methods in them. You can do generic programming just like in C++. We have an algorithm library as well, which is part of the standard library, which does all of the stuff you'd expect it to with algorithms. So generic programming also works. And there's no compromise in runtime performance, just like in C++. Now, some of our defaults are different because we value memory safety more. But the thing is, you can always make it faster. You can always make it just as fast. And given that there are LLVM and GCC backends for D, there is no reason why D code would be slower anyway. It will produce the same code. And if it doesn't, it's a bug. So how is D not like C++? Well, the big elephant in the room is that it has garbage collection. So when I was asked about if those arrays were static and I said they were dynamic, how do I append? Where am I getting the memory from? The GC. That way I don't need to care. So there was no free there. There was no allocators. You didn't see anything like that there because you don't care. You just leave it to the garbage collector. Now, we'll get to the garbage collector in a bit. Metaprogramming in D is a lot simpler than in C++. I will show you an example, and trust me, I have done insane things in C++. It is easier, a lot easier. We even get comments from people saying, I think I understand templates now because in D I can do them, in C++ I can never write them. There are modules, and yes, C++20 has modules, but no compiler supports it yet 3 years later, which is showing how difficult it is to support given the current language. They're also weird in all too many ways because of backwards compatibility and dealing with the preprocessor, the fact that namespaces already existed. I mean, I understand why, but it is complicated. And again, not even available yet. It's a lot faster to compile. If you write Java-like code, it compiles like that. But if you start adding templates and compile time function evaluation, it starts getting slower, but it's still faster than C++. But then again, that's not really a high bar, is it? And it's just simpler and easier. And I'm saying that, and you'd say, well, you're biased, you're the D co-lead. Right, but how did I get here? I wasn't born D co-lead, it didn't run in my family. I picked the language after C++ for a reason. And it's because I write less code and it does more. I mean, I struggle to write a project in D that's over 2,000 lines long. I don't need to, ever. It just doesn't happen. So, the GC gets a bad rap, and I don't know why. And I've learned to just keep calm and use the GC and trust it, and it's fine. And this really is interesting to me because I both don't get why people have this instinctive reaction to it, whilst at the same time knowing that I did as well. And the first thing I thought when I read the deprogramming language book was, I like this, but this GC thing doesn't sit well with me as a C++ programmer. But it turns out I was wrong on a bunch of things, and I had a lot of wrong preconceptions. So let's maybe dispel a few of them. First of all, GCs are not magically slow. This barely makes any sense anyway. You could write a garbage collector, and people have done, in C or C++, and then write a program that only allocates on that. Does that make C or C++ slow because it has an implementation? No, that doesn't make any sense. It's the same thing here. It's just there's a GC written in D that some language constructs lower to, but you can avoid them. You don't have to do them. Secondly, reference counting is a form of GC. If you have a bunch of SED shared pointers, for instance, and you have a big graph or a circle, when one of the ref counts goes to 0, guess what? Doom, 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 pause, just like a GC would. It happens. It depends on your graph, of course. It depends exactly how data relates to each other, but it is a form of garbage collection. It has different trade-offs. And in languages that can't tell the difference between something that's shared or not, you always have to lock when you increment or decrement the reference counts, which is a penalty that you pay for no reason, especially if your program is single-threaded. But there's no way for the library to know. There is indeed, by the way. And safety by default is preferable, I think, because it's unlikely, well, you're not going to know what the bottlenecks are. I've only run a profiler once in my life when the bottleneck was exactly where I expected it. Every other time it was somewhere else. In fact, I remember the exact name of the function that was slowing down the program the first time I ran a profiler. It was printf. All I had to do is comment that out, and the program ran 100 times faster. Not something you're going to intuitively figure out. So if allocation is where you're losing all your time, and if you run a profiler and that's why you know that, then you can think about doing something about it. But the chances are it's not going to be. And if it is, you can get around it, and at least you have a working program now instead of something that crashes. And the other thing is that malloc and you are slow anyway. If you're doing malloc in a tight loop, you're going to slow down your program. People don't do that in games or anything that requires real time because you can't know how long even malloc is going to take to return. So there's that. And the GC in D at least works this way. When you allocate a GC, then you might have a collection. It doesn't randomly happen in the middle of your program. It's unpredictable because you don't know what the allocation patterns are going to be. But if you don't allocate that much memory, it's never going to collect. So a D program that doesn't allocate a lot of memory and runs in 10 milliseconds is going to run faster than the equivalent program in C++ or Rust because it's never going to free the memory. It just goes, operating system, take it. I don't care. So you don't need to free the memory if you never hit the limit. So it could even be faster. It isn't usually, again, it depends on how much memory you actually allocate. So it only collects when you allocate. Basically, you allocate and it goes, I don't have enough memory now. And then it does a collection. But even that's controllable. You can turn the GC off for critical sections and turn it back on later. So it collects then. You can tell it to collect when you want to. And there's even, I forgot to add to this slide, an annotation called @NoGC that will guarantee a compile time that the code that you're writing does not allocate into GC, if that happens to be something that you care about. Now, I have to say that there are situations in which you cannot afford allocating to the GC. They exist. Real-time stuff, for instance. But they're few and far between, and they're a lot fewer than people think they are. I can't afford a GC. You probably can. You might not, but you probably can. And again, you can get around it anyway. You can call malloc from D. Nothing's stopping you. I wrote a vector struct in D that uses allocators. Doesn't use the GC. It can be done. The thing is, you throw memory safety out the window then, and things get interesting fast. And by interesting, I mean GDB. Now, metaprogramming C++. This is code I wrote, and I'm not proud of it because look at it. And what this is trying to do is basically concatenate a bunch of strings at compile time variadically. So the strings can be any length, and you can pass in any number of strings to it, actual just regular C strings, which are arrays of character. So I'm using a variadic template to deduce the length of the arrays that are passed in variadically. Yeah, that was my first Stack Overflow question because I couldn't figure out that syntax because that doesn't make any sense anyway. Those ... I knew had to be somewhere, but apparently there, and with the parens. So I wrote this because somebody challenged me at work to do this at compile time, and I dropped everything I was doing and just worked on this all day because I'm nuts. And this is one of the functions inside the insane thing. And if you're curious, you can click on that link and find out the rest of it. So I did that, and somebody went, well, how would you do it in D? I went, it's so boring, I'm not even going to bother. It's this. Take a bunch of strings, return a tuple, we're done. Hardly any syntax. The syntax that you need to know here is that D declares templates with double parentheses. So the first set will be the template argument, and then the second parentheses will show you the runtime parameters. So here's just a variadic template. So however many things you're passing me, and then declare again strings, and then return a tuple, and we're done. And yeah, that's how it looks in C++. So this required breaking my brain and asking Stack Overflow. This is trivial, and what's the point? I was asked that stuff about concurrency in D. So D uses the actor model, and this isn't particular to D. This is basically what the actor model is for somebody who doesn't know. Like object-oriented programming, everything's an object. In the actor model, everything's an actor. Of course, that's not the case in D. We just use that for concurrency. What actors can do is send messages to other actors, so they have an address of some sort that they can send. That's how they know. So you decouple the two by sending a message between the two. I only know somebody's address. I send a message. The runtime takes care of sending it over here. And then they can create more actors and decide what to do for the next message it receives. So it's basically, it's more object-oriented in the sense that Alan Kay meant it than object-oriented programming ended up being. So you send messages and then they're all concurrent. They can be in different threads. It depends on the model you're using. They could be in green threads or system threads. Doesn't matter too much for the actor model. But this way, you don't lock, right? You don't need to lock because there's nothing to lock. They're not sharing data at the same time. You send a message, it's gone, somebody else receives it. Of course, this has to be locking in the implementation. And this is an example. I ran out of space, so there's one curly brace missing. So what we're doing here is spawning a thread. And I'm spawning a thread and passing a function to it, writer, which is below. We'll look at it in a bit. So this is just a function pointer. And it returns something we call the thread ID, because again, we need to know the address to send messages to. And then we're looping from 0 to 100, not including 100. So this is an example of the for each loop I showed you, talked about before. So instead of doing the traditional for loop, this is a lot easier to read. And then we're just writing that we're in the main thread and the counter. And then we're taking that thread ID and sending it a message and sending our thread ID so it can reply to us. And then also the integer. And then we're going to wait by saying, I want to receive, but the only type I'm going to receive in terms of messages is a thread ID. I don't want to receive anything else. If somebody sends me an integer, I don't care. That's not for me. And then in writer, we loop forever, essentially. And then first we synchronize with the main thread by another receive only. So I only want to receive a tuple of thread ID and int, which is what we're sending above if you take a look. And then that's a tuple, which has two things, and you can index them by 0 and 1. And then it writes, I'm in the secondary thread. The second, so index 1 is the integer we send. And then index 0 is the thread ID, and we send a message back saying, we're done. So that is a synchronization done there. There's no locks here. You just send messages. It kind of works. So this is an interesting way of doing things. It isn't the only language that does this. There's a language called Pony that has some really interesting things in regards to actors and actor model as well. And Pony doesn't even have deadlocks because they don't have blocks at all in the language. It doesn't exist. And it's proven mathematically to not lock, to not deadlock because things are safe. And D has shared and immutable because here, what we sent was thread ID and an integer. Can't remember what thread ID is, but it's probably some sort of pointer. And so that's fine, well, kind of fine. The integer is definitely fine because we sent a copy of it. But what if we're sending a string or an array of characters, for instance, an array of anything? And what if this thing is globally declared somewhere? So threads could be writing it to at the same time. This is not good. So in D, we stopped that with shared and immutable. Immutable data can always be shared because it's immutable. Nobody can change it by any alias. So it's fine, share all you want. Nobody's going to change it. They can only read. There's no data races if nobody's ever writing. And shared data, you can send to another thread, but you can't really do anything with shared in D. It's a massive pain, and that's on purpose because normally what you do is lock a mutex and then cast away shared, do your stuff, and unlock the mutex. And there's libraries to make this easier. But the way we're trying to move it to in the future is structured concurrency. This is something I've only known about for a very short while. A colleague of mine discovered a paper that somebody wrote for C++, but it's not a C++ idea. It's a lot older than that. And the idea is that this is to concurrency what structured programming was to using GoTo. So in structured concurrency, spawning a thread and joining threads are like go-tos, not something you should be doing manually. Like under the hood, that's what happens, but you write a for loop, you don't go to the beginning. It's similar here. So you make sure that all the threads join by giving an operation to a thread pool, for instance, and then waiting on the whole result, all the threads join in and you get the result back. There's some complications here with canceling threads because something bad happened, that kind of thing. But in short, don't spot threads, don't join them, use the structured concurrency library. And I'm trying to get the author of the D version to introduce it into Phobos, because I think that that's what we need to tell people to use instead of low-level, error-prone things like that. Just like don't use new and delete in modern C++, use unique pointer and shared pointer, similar. And because it's a compute forum, I figured I might as well say something about that. I did not write this code. I just copied it from the compute package. And it's basically how you write D code, you write kernel in D, and then it has backends for OpenCL and CUDA. And it's the same D code that will get run on both of those. And this is an example of some algorithm that apparently is famous. I don't know. It's annotated with this thing called kernel, which is one of the features of D I forgot to mention, which is annotations and things that can also be anything. It can be types, it can be values. You can do your own annotations, and then you can reflect the compile time and figure out what's going on and do things based on that. So you write a kernel this way, and then you schedule it to run this way, and the equivalent CUDA code is there commented out in the last line. So this is possible in D as well. But I don't know too much about it. I just know the person who wrote it. And so how D could benefit CERN going forward? Well, it's a lot less code. And less code means less bugs. And less tests, fewer tests to write because it's less code. And it's fewer bugs anyway because the language makes it harder to write bugs. So certain classes of bugs just don't really show up that often. And far fewer, if any, memory safety bugs. If there are, it's because you're allocating memory yourself, probably. Because if you're allocating the GC, the memory lives forever, so you can share it as much as you want. It's fine. It never goes out of scope. If it does, it'll get cleaned up. The runtime performance is at least as performant as C++. Every single time I've done a benchmark, D has either been the same or beaten C++. Sometimes implementations are the same, but if there's an implementation of a protocol already and I write my own, I'm not gonna, it runs fast. Now, having said that, the reference compiler doesn't produce the best code, but there are, like I said, LLVM and GCC backends. So they produce this code as well as they do for the equivalent C or C++ code. Because the same backend, why would it be any different? And compile time reflection makes binary protocols easy. So way back in the day when I worked here, there were, obviously binary data read by the detectors, and the formats were being designed as we went along, and every test run it was different, and it was 4 bits of this, 8 bits of that, and bit shifting and blah 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 and blah blah blah. And I did a lot of that. I don't have to do any of that in D. I wrote a library to serialize things in binary. You declare a struct, you put some annotations there, gone, done. Deserialize this, and it's done. Even when some of the times the fields, so a lot of the times in these protocols, one of the fields will say length, and then the length of the bytes that you get after the header depends on this thing. I even wrote an annotation to do that, so I didn't have to write the code, and it works. If anybody knows what SNMP is, Simple Network Management Protocol, I wrote enough of it in the morning to write a test because it's easy enough in D. Now imagine doing that otherwise. I wrote ICMP in less time than that. I just declared a header and that was it. I'm sending packets. So a lot less work, a lot less error prone, because if any bugs occur, they're in the library, not in user code. The less code you write, the better off you'll be. And future developments in D, right now we're concentrating on stabilizing the language and fixing bugs. So anything that isn't working too well, we're really concentrating on that instead of adding features. So we're kind of in maintenance mode now. I want to finish version 1 of Phobos, which is a standard library. Why is it not finished? Well, we have allocators, but they're in std.experimental.allocator, and they have been there for years now. And I'm trying to figure out if I can cast this API in stone so I can, move it out of experimental. There's a few things going on there too, which are really interesting. And I broke my brain last week thinking about allocating things. So there's that. I'm also working on the proposal for language additions. So Rust has this. They have several editions of the language in which you opt into a new edition and then things change. There's a proposal for C++ for this too, which I'm probably going to base myself more on because it allows for breaking changes. So what we want to do is fix the mistakes of the past without bringing people's code. We want old code to always compile, but how can we do that and move forward and shed the baggage of the past? I think the language additions are the only way that we're going to be able to do that, especially if we're going to cut features, because that's easy. Just cut them, and the next edition, it won't compile. And then after we finish all of that, figure out a way to do version 2 of Phobos and move it forward, because there's also mistakes made there. SCD JSON is not great. SCD XML is not great. And we need better versions of those libraries and with a lot more batteries included. And then hopefully world domination, who knows? So let's conclude. D is beautiful and powerful, at least I think so. Beauty is in the eye of the beholder. D has nearly all of the features of C++. I know because I wrote a translator and I stopped when I realized I couldn't translate SCD as reference free. D has features C++ does not. D requires less code to do the same thing. And I know this from experience because I've written a lot of both. Metaprogramming in D can be done by mere mortals. And D produces performant code, so that's not going to be a worry. And one language to rule them all, in this case here, means you can do low level, or you can write Python-like code. You can write a script in D that's just, throw away, and it will have type annotations compared to the Python equivalent, and it will take slightly longer, but it can go all the way down to low level and crazy things and metaprogramming and etc. Or OOP. And if anything, one of the criticisms we get is that it's the kitchen sink. It's got everything in there. But it means we don't impose any style on anyone as well. I mean, there's people that only write classes. I barely ever write classes. In fact, if it were up to me, I'd remove them from the language because they're not needed. And the reason why they're not needed is, do I think OOP is a bad idea? No. But in a language with compile time reflection, you don't need it. I wrote a library to prove you don't, because you can just do the same thing with structs and generate the virtual tables in the file. And then you can control the layout, which you can't if it's baked into the language. So you can give the user options like expanding the virtual table pointer into not being a pointer, just a bunch of function pointers, placing it elsewhere, a bunch of other things. So it does stride all of these different levels. And I think the other thing that's really hard when it comes to selling D is the fact that it's not obvious from the list of features. It's the way they come together. And you have to write enough code to actually figure that out and how things aren't getting in your way. Things I didn't mention, like variables are initialized by default. The number of times it saved me because an integer is 0 and I could just add to it instead of random garbage in the stack, for instance. And they all come neatly together and it makes refactoring easier. Something that somebody else said is that D is very plastic. So it's easy to mold into what you need, into what you want. And I guess it's question time. Thanks.
Thank you very much. Very interesting talk. So any questions to Atila? Atila, please.
Yeah. So thanks a lot. As somebody who knows practically nothing about the language, I was just curious to see what is it all about. I have lots of questions, but maybe just
go for it. That's why I'm here.
But maybe just sort of a large scale question of I'm not entirely sure how the build procedure of a D project goes. So this also leads into like cooperation between D source code and some other source code, because I actually got a bit scared about your statement that, well, D, the one thing to rule them all, because yeah, in physics code, that's not really a viable route. I also don't like how Julia tries to implement everything in Julia in one go, because it can't effectively use existing C++ code. So can people compile a library in D
yep.
and then call into it?
Absolutely. Just the same way you do in C or C++. And I mean, you call into C code very easily too. Before, you'd have to write the declarations in D syntax. Then I wrote a program to do that for you, and then Walter went and implemented import C, so you don't need to do that anymore. So if it's a C library, just import a C file that includes the headers you want, you're done.
Okay.
And you call into the C library just like you would. You just link, like if you have something pre-linked, you can do that too. If you have a shared library, you could just link to that thing there, please. So in terms of how it builds, object files, shared objects, exactly the same as anything you'd see in GCC or Clang.
Because so I know that fundamentally a language that has built-in garbage collection or built-in some sort of memory management is always a bit tricky to interface with, like the rest of the application.
No, the only time that is true is when you're interfacing with a language that also has a garbage collector. That's when the problems start. Because C#, for instance, which garbage collector is going to free what? That's a problem. So in that case, we need to write GC free code to be able to pass these pointers to C#. But if you're passing it to C, in all likelihood, I mean, any library in C basically has a function to create things and then a function to destroy things. You just do that. Because the GC isn't going to do anything to those pointers.
So how do you build D code? Because you mentioned that documentation is built by D and tests are built by D. Do you build it with CMake? Does it have its own build system that you have to use?
You could. People have done try to use CMake. I would recommend it. People also try to use Mezen. Wouldn't recommend it either. Normally what happens is, for most projects, because they're simple, there's a package manager called Dub. This is equivalent to pip in Python. And so Dub has its own build system. Now, unfortunately, not a very good one, which is why I wrote a different one. But for the most part, people use Dub because all they're doing is, there's some code here, and they declare the dependencies they have. They'll fetch them off the internet, build those, link, done. But you can do whatever you want, because the compiler works just like GCC or Clang do. You can go build this D file, build this D file, and then link them all together. Although I did some experiments back in the day, and I have to redo them with current hardware. In D, it turns out to be faster to build per package. So package in the sense of a Java package, so everything in a directory. Because the ways that modules import each other end up making this faster than per module. Because you'll need to rebuild them anyway.
Okay.
But basically, building is not hard. If you go, like, even the flags are very similar. You go dmd-c d file, you'll get an object file.
Okay, but you know that building for us usually means building millions of lines of code and producing gigabytes of binaries. So I was wondering if D has any project that
at that scale?
That level, yeah.
There's a company called Weka in Israel, and they're doing a file system that's distributed. And at least the last time I heard them talk, it was the fastest one in the world. And they use D, and yeah, I think it's over 1 million.
A file system that needs gigabytes of libraries.
I don't know. You'd have to ask them. I don't know. All I know is that they have that scale. I think we have at Symmetry maybe 200,000 lines of code.
Okay. I'll let other people do it.
Okay. Any more questions to Atila? I see people remote. Bernard, you turn on your camera, so you have a question, or yeah?
Yeah, but Philippe raised his hand first.
Yeah, but okay, fine. Okay, Philippe, go ahead.
My question was, how does
I think he froze.
Okay, maybe we take. Let's see if Philip comes back. No, he's stuck. Maybe Bernhard, you sneak in.
All right. I have a couple questions. Some of them Atila already raised before. Let's start with this one maybe. You presented the C++ version for my-make strings, and you concatenated reference to string literals that you made erratic, and then you said, well, the D version is super easy, and you just had the string in your type there. Does that perform a copy of the string? And how do you express like references or values, and how do you move and forward, and is that needed, or if it isn't, why isn't it needed? And is there a thing like last use, like move of last use, like Rust has? Like how does the ownership get transferred?
Okay, so the copy thing doesn't really matter because this is a compile time and I don't care because it's not good in runtime performance, so it doesn't really matter. Secondly, well, let's get to the move thing. There is a way to move things. There are no R value references in D. The way we do it is you just write by value. So it looks more like in Rust, and that's a move. Now, there's some problems there that somebody's working on with the move semantics, but that's what a move is. So you can have non-copyable types, just like in C++, that need to be moved. But we avoided the R value reference problem. What was the second thing?
Yeah, that already answers a bunch of those. But then you said like here, my make strings, you don't care about the copy because it's compile time. But I could call my make strings here on runtime string values.
Yes, you could.
And that would pull copies of those strings.
Yes, but strings in D are slices of characters. So what you'd be copying is a pointer and a length anyway. Like
that's all right, but like in that sense, I could see that the C++ version could be more optimal.
Yeah, again, I was doing this a compile. That was a template anyway.
Right. Okay. You mentioned in another place that if like D could be faster with the GC because at the end you could just hand back the memory to the operating system. You don't need to deallocate anything. In that case, who runs destructors? Well, like I assume your types can have destructors.
You're right. Well, just like in Java, you can't rely on things that are on GC having the destructors run. But the thing is, people don't usually write types like that and put them on the GC. Usually structs, like in C++, are on the stack. So whenever they go out scope. But if you do put them in the GC heap for some reason, then yeah, you're not guaranteed they're going to run.
So if I make an array of file handles in D, like I could not rely on when those files would be closed.
Not if you put them in GC memory, no.
Which the array syntax that you presented would do by default.
Yes, but I'm not sure why you do that. But yes.
Because I need an array of files. Okay. And then maybe this is the last one. Why would I pick the D language over Rust? So I just checked like crates.io on Rust. There's like 100 times the packages that Dub has available. It just feels that the Rust ecosystem by now is larger.
Sure.
Given I would need to move off of C++, why would I pick D over Rust?
Well, that's a good question. And ecosystem is definitely something that needs to be taken into account. So if there are packages there that you need that you can't find, that might be an idea. Now, do remember, though, that you can always use C libraries or C++ libraries, depending on the API, for the task at hand. So you might not need native solutions. But the main reason I would pick the and over Rust, because I like Rust. I think Rust has done something incredible. I just think that what they did is pointless because they ensure memory safety without a GC, but that's like saying, how do I lose belly fat without lifting weights? Why would you do that? You're just playing on hard mode for no reason.
Well, it's a different approach, but we could have a lengthy discussion on this.
It is, but try writing a linked list in Rust and also try doing
log-free algorithm. Unsafe. That's right.
Right.
Yeah. But
try doing
log-free linked lists, yeah?
Or log-free algorithms in Rust because the GC makes them possible.
Terrible. Right. Okay.
Again, it's just easier.
Okay, thanks. Philippe, please go ahead.
So my question was, how does interfacing D with existing C++ library look like?
Right. So our story there is probably better than any other language out there because we have the syntax to do it. So you can declare C++ classes with extern C++ in D and then call into C++ code. You could even use templates. You can even declare constructors. I've done all of this. But you can't do everything. So if it's a template header only library like Eigen, then you're going to have a bad time because some constructors are just not representable. But if the C++ code is simple enough that regular classes, that kind of thing works, you can write the declarations, call it to C++, and it works. The name angling works, namespaces work. It's the only language I know of that can call C++ that isn't called, well, either C++ or Objective C++.
Fair enough. Thank you.
Okay, I saw a hand up, Andrea, in before, but it's
yeah. Thanks.
Sure.
Bernard stole my question about trust, but I wanted to thank the speaker. Thanks a lot, Atila. This was extremely interesting.
Thank you.
Maybe since I'm speaking, just for curiosity, I was just browsing around. What's the situation of the compiler? I see that there is DMD and also LDC. So is there already more than one compiler? So
right. So DMD is a reference compiler. So that's the one that's the main work that goes in. It's got its own backend because Walter Bright originally wrote a video game, and then in the 70s, if I'm not mistaken, and then he wrote a C compiler, and then made money off of that, and decided that C++ sounded like a good idea to differentiate his compiler, and he thought it would take a month. It did not. But Walter is one of the few people that wrote a C++ compiler from scratch. The only person that wrote it by himself, in any case. There's only been like 4 or 5 C++ compilers ever created. I'm getting away from myself. What was the question again?
It was just what's the...
Right.
Yeah.
So because of that, he had his own backend to generate code for DOS and then Windows later. So DMD uses that. So the front end is what it is, and then the backend is his own that came from his own compiler. Well, LDC and GDC, by the way, are the same front end, but glued to LLVM or the GCC backend. So that's what LDC is. The same front end with a few changes. There's a patch on top that compiles to, well, basically binds it to LLVM. And then GDC does the same thing for the GCC backend.
Thanks.
Maybe a question that... yeah, sorry, because it's closely related. So what is D a standard, or is it the reference implementation that dictates language?
What do you mean?
So if LDC and had a different behavior than the reference implementation, is there a standard to disambiguate, or is it the reference implementation that dictates?
No, there is a reference. Now, the problem with these things, as always, is if you only have one implementation, then you never know exactly whether the reference is lacking or not. You need someone else to be able to implement it and then start asking questions. Same things happen with protocols. This is why people tell you all the time, do not ever write your own TCP stack. You'll get it wrong because it needs to be bug compatible with the internet, and it won't be. Because if you just read the RFC, it won't work. Trust me. So this is an issue, but yeah, it's hard for me to know when it's going to differ. Because there's no other front end. There is one being worked on right now. There's, well, 2, but none of them are anywhere near production. But they won't have different semantics because they use the same front end anyway.
Andrea, another hand. Please go ahead.
Thanks. Just since I thought about it, is there? What's the usage of D now? I mean, is it especially, I don't know, in the scientific world? Are you aware of some large use by some scientific communities or other communities?
We have had speakers from scientific communities before. There's this guy called Ilya, I forgot his surname. He wrote a bunch of algorithms for computational work. They're the Mir libraries, Mir algorithm, and there's a lot of stuff in there that, you know, he has a lot of experience with NumPy and pandas and that kind of thing. So people have done it. And in a hedge fund, a lot of these calculations need to be done as well. So we're using it.
Thanks.
So maybe one very specific question. Do you support vector instructions through intrinsics, auto-vectorization, these kind of things? Okay, great. Any more questions to Atila? Remote? I don't see any. Okay, so thanks a lot, Atila, again, for the very nice talk.
Thanks for listening.
And yeah, the recording will be online soon then.
Cool.
Okay, thanks, everyone.